Muy buenos días a todos y a todas. Muchas gracias por estar acá para la charla que nos va a impartir el doctor Leonardo Lalicata. Muchas gracias, Leonardo, por estar acá en las celebraciones del 50 aniversario de la Escuela de Ingeniería en Construcción del Tecnológico de Costa Rica. Leonardo, les cuento que para la parte de la presentación técnica, pues la va a realizar en el idioma inglés, pero tiene un manejo menos técnico, pero manejo del español, o sea que sí puede entendernos las preguntas, así que se pueden sentir con toda confianza preguntar ya sea en inglés o en español al final de la presentación. Les cuento que el doctor Lalicata tiene experiencia en temas de ingeniería geotécnica, sobre todo modelando con modelaje físico y modelaje numérico, además con algún tipo de herramientas computacionales para el análisis y la visualización de métodos experimentales en el área de la ingeniería geotécnica y de los ensayos con centrífuga. Obtuvo su doctorado en la Universidad de Roma en el 2018, su maestría en Ingeniería Civil en la Universidad de Roma en el 2014 y su bachillerato en Ingeniería Civil en la Universidad de Roma en el 2011. Así que los dejo con la presentación del doctor Lalicata. Muchas gracias.
Venga, muchas gracias y buenos días a todos. Y gracias a Rafael por invitarme a tener esta charla, esta clase. Y como digo, ahora voy a pasar al inglés, porque no puedo dar toda la clase en español. So, the talk of today is going to be about Earth and structure and how they can be a possible answer, in my opinion, at least, to climate change. So before starting the presentation, I would like to tell a couple of words about myself, about my experience in geotechnical engineering. And as Rafael said, I defended my PhD in 2018 at the University of Rome La Sapienza. And during the PhD, I've been working on the soil-pile interaction under unsaturated soils, both via centrifuge modeling and also via advanced and fully coupled numerical models. And this was also the topic of the first postdoc there at University of Rome La Sapienza. After that, I moved to the city, University of London, where we developed a novel type of piles. So always still working on deep foundations. So this is the pile we developed, which is called the impression piles. And this type of pile is able to provide like an increase of 40% in capacity under axial load. And we have been working on both centrifuge modeling, as you can see from this picture. I was assembling a model here, but also we managed to upscale the problem to the real scale. So this is the tool that you will use on site to build this type of piles. And since 2022, I am an untenured assistant professor at the University of Genova in Italy, northern Italy. And here I have started to study the hygrothermal behavior of earth construction. And this is going to be the topic of this talk today. So the objective of this talk, the outline is reported here. I wish I will be able to give you a background on raw earth construction materials, as well as some of the mechanical aspects and the hygrothermal coupling in this kind of materials. Finally, we will also obviously have some sort of conclusions. But before that, it's important to think why we want to study and improve the performance of the building sector. Well, first of all, because the building sector, it takes between 20 and 40% of the total energy consumption in Western countries. And in the European Union, this 40% of energy consumption corresponds to the 36% of carbon emissions, which means that there is a huge space to improve our buildings and our construction in order to tackle climate change. And we must be clear on that. With building sector, both residential and commercial, we include all, which means from the product, so the sourcing of the materials and the construction, transportation, operational use, and waste of the waste of the material and buildings in general. And one very important reason to study raw earth is that this is widespread all around the world. As you can see in this picture, these orange areas are the areas where there is earth architecture. And you see it's very common in Africa as well as in Asia, but also in Europe and in Central and South America. And another important thing to mention from this picture is that a large number of UNESCO World Heritage Sites, they are made partially or in total in raw earth, in earthen materials. So there is not only an interest from the construction point of view, but also from the preservation of the historical monuments and preservation of our heritage to better understand how this structure works. And these, I've just collected some nice pictures of the UNESCO World Heritage Sites, as you can see from this city in Shiban, Yemen, which is more than 2,000 years old. And this is called the Manhattan of the desert, because these high stories building, they are like 8 to 9 stories each one, and they look like a skyscraper profiles in a way. But also there is this mosque here in Mali, which has been built in the 13th centuries. And on top of that, we have also this fortified city in Morocco, as well as the world famous Alhambra Castle in Granada, south of Spain, which is from the 10th century. So it is also, that one is 1,000 years old. And finally, there is also the very world famous Great Wall in China, that has some sections that have been built on rammed earth, so which again is another technique of raw earth construction. But we have not only World Heritage Sites, we have also dwellings. As you can see, here I'm reporting an example of a school built in Germany at the beginning of the 19th centuries that is made in adobe and a roof. But also there are a combination of dwellings and UNESCO World Heritage Sites, such as the city center of Cusco in Peru, where the whole center is built on adobe walls. Buildings are made of adobe walls founded on stone foundations. And this belongs both to the Aztec Empire, but also to the Spanish period. So they both use the same technology because it was working really well in that area. And recently, the rammed earth has been rediscovered also from design studios. And you see from this example, this is used all around the world at the moment. We have example in Australia as well as in Austria, and also some more on the frontier, if you want, applications, such as this 3D printed circular house made for an African project. This has been built in Italy, and it is noted that this 3D printed house is printed in mud bricks. So it is earth, which is 3D printed and sprayed. So, but what is raw earth? So the raw earth is a construction material which mix soils and water, and then is put in place trying to pass for the least possible transformation. During the centuries, there have been developed a number of construction techniques which have tried to summarize them here in the slides. So we have the adobe, first of all, in which you prepare your brick in some formwork, and the soil is mixed with a high water content. So the soil is in a plastic state. And once the brick is dried, you can assemble your wall. Similarly, we have the cob, in which we mix water, soil, and straw to build our freestanding walls. And this is particularly used in Northern Africa, for instance. And then when this the material dries, you can build up the second part of the building. Finally, well, not finally, we have also the compressed earth bricks, in which the water content is much lower than in the other two cases, and you increase also the compaction energy. And as you can see, you can use these bricks like a Lego, because you compact them in different shapes, such as they can better fit one to each other and build a stronger wall or a stronger structure in general. And finally, there is the rammed earth. So rammed earth is a technique to build freestanding walls by compacting layers of soils at the optimum water content in formworks. And when the material dries, you can remove the formworks and proceed with your construction. So at the beginning, I was talking about the building sector. And building sector, as I said, we must intend the general process. So not just our buildings, but also what are the materials that we need to construct our building. Then we need to consider also the construction, transportation, use, life cycle use, and finally the end of life. And it can be shown that rammed earth can help and reduce the carbon emissions at all stages of the life cycle. For instance, in terms of product, well, by using earth, which means that earth can be usually locally sourced and also requires a very low manufacturing energy. Just for giving an example, in terms of construction, you need 60% less energy to build the same dimension brick compared to a fired brick one. So there is a significant savings in terms of energy required. And if you want to compare that energy to the energy required to build the same structure by using cement-based alternatives, what you find is that you need approximately 1% energy compared to the cement alternative. So, which again is a massive decrease and a massive importance of carbon savings in this term. But first of all, let's try to go a little bit in the detail on the mechanical aspects of raw earth. And as I said, raw earth is made by soil mist mainly. And the soil, the first thing to notice is that we cannot use all the soils because not all the soils are suitable to be used as a construction materials. And there are standards and rules that tells us which is the particle size distribution that our soil should have in order to be used. And as a general way, you should have like between 5 and 35% of clay, 10 to 25% of silt, and so on. Approximately 40% on sand, and then what is left can be gravel. And after that, as I said, you need to prepare our bricks or our walls, and typically you compact your samples to the optimum water content, for instance, which is the amount of water that gives you the higher density at the same compaction energy. But after that, once you have prepared your brick or your wall, you need to wait that for to cure, which means the drying process in which the bricks dries, and in this case you can have some shrinking, and this shrinking can induce problems in terms of quality control, repeatability of your results, and then your structure. And this is very important if you want to apply that systematically. One option to reduce that, so you see your points will move from this curve in here, and they will go on the left, because the sample will lose weight and lose water content approximately 3–4%. And you see there is a lot of variation in this data. One option is to increase the compaction energy. For instance, these points here, we are increasing the compaction energy, and then also the drying, the curing process induces a much lower change in density and also in shrinking, obviously. But another beneficial effect of increasing the density of our samples, of our bricks, is that we increase exponentially the compressive strength. That, as you can see, of normal compacted, proctor compacted earthen materials, the compressive strength is about from 0.5 to 2.5 megapascal. But if you increase the compaction energy, so increase the dry density, what you get up to 10 megapascal of compressive strength, which is more than suitable for construction purposes. An alternative to increasing the energy, because maybe you don't have the resources to do that is to use stabilizers. And there are standard stabilizers such as lime or cement, but also recently they are developing novel biopolymer stabilizing. And what they get, usually, you get an increase in the compressive strength with the stabilizers, which is less marked for the biopolymers. But in general, you get an increase in the compressive strength. But also regarding the effect of the recycle of this material, because earth, you know, is virtually you could reuse that a number of times. So in this study, which is made by Brun et al., they also, after testing the samples, they crushed them and built novel samples to test the influence of eventual degradation of the compressive strength upon different cycles. And what they get is that the standard unstabilized earth did not reduce its strength with the number of cycles, while on the contrary, the stabilized with 4 or 8% of cement, the stabilized earth, you have a reduction in the compressive strength, and this is because you are basically breaking the bonding that the concrete gives to the materials. And on the other side, the biopolymers, they show a slight increase in the compressive strength, but this is because the curing process of the biopolymers is much slower. So there is something that is still curing over time during these cycles. But the important result in general is that you can use and recycle raw earth both in stabilized and unstabilized conditions. The problem with the stabilizers is that they increase the carbon emission consumption, and possibly they reduce or even drop to zero the environmental benefits of using raw earth. So you need to find the equilibrium between the compressive strength and the use of stabilizers in this case. So I hope I give you an overview on how raw earth can tackle climate change in terms of product, construction, and also end of life, such as reuse, recycle, and disposal. What is missing in this picture is the indoor comfort, which is the operational use. What happened during the operational use of a raw earth building? Well, if you look on the literature, what you find is that raw earth is known to be an excellent hydrothermal regulator. And here we need a bit of definition, I'm sorry. So with hygroscopic regulator effect, which means that the wall is capable to absorb and release moisture depending on the current ambient humidity. And this is possible because of the open network of nanopores that they are present in the earth materials. As a consequence of this, there is also a thermal regulator effect because the evaporation condensation processes that occurs during this absorption and release of moisture, they need energy. So during evaporation, the soil tends to absorb the heat from the atmosphere that is released during the condensation phases. The problem with that is that you can find only qualitative assessment of the hydrothermal performance. And this for a very simple reason. First of all, because laboratory experiments as well as field investigation are time-consuming, very expensive, and also difficult to control, because it's actually a nightmare to control relative humidity, both in a climate chamber, but also obviously on site. So for that reason, it's not really easy to find a proper assessment of the hydrothermal performance of earth materials. And one option to overcome this problem is to adopt numerical and constitutive modeling on the hydrothermal coupling. And this is actually my topic, Genova, and now I'm going to show you a little bit of an insight on what happens during this coupling. So first of all, with coupling, we are thinking on the complex interaction that is happening between the three phases in the wall, so the solid, the liquid, and the gas. Liquid and gas are water, so we have liquid water and water vapor, while the solid in our model is just a rigid structure which influences the results in terms of porosity and obviously on thermal properties of the grains. And in these problems, we need also to account for the phase change between the liquid water and the water vapor that can go from one side to the other. We need obviously to account for the heat and moisture flows at the boundaries. And so in conclusion, we need to solve a system of two equations, one for the temperature and one for the water, in two variables. And these two variables are in general the relative humidity for the water and the temperature for the energy balance. To these two, we need to include, I'm sorry for that, another equation, which is the well-known Kelvin law that links suction, which is potential energy, but is also the negative values of the pore pressures in the soil, in our material, that links suction to temperature and relative humidity. And with these two and the Kelvin law, we can write our water mass balance. That is this awful equation, which is made a number of terms. But basically, what it's saying here is that we have a storage term for the liquid water plus another storage term for the water vapor mass. That is must be equal to the fluxes, the liquid water flow that follows the the generalized Darcy law for the liquid flows, and the water vapor flows that obeys to the Fick law. So this is a diffusion process through the medium. Sorry. In terms of thermal balance, the equation obviously it has the same shape, but here the storage term in this case is function of this heat capacity of materials, but the flow is given by the conduction that it is described by the Fourier's law, and there is also another term which is often neglected but is very important in our case, because this is the energy required in the phase change process that obviously is a function of the latent heat of evaporation of the water. But now, the first thing I've tried to do when the first time I saw this equation, wow, this is very complicated. Let's try to find a way to understand what is important and what is not. And this is this insight I'm going to give you now. This is the work of the last 1 year and something, and that's been published in some papers. So first of all, I have been focusing on the water mass balance, and in particular on the importance of this term here, which is the water vapor mass, change in mass, compared to the change in the liquid water vapor. And what we found is that in most of the application, the changes in the water vapor mass is much smaller than the changes in the liquid water mass, which means that is negligible. And if that is true, we can cancel out this term that really simplifies our life and our equation. Well, one very simple explanation for that, even though there is just a vapor fluxes in our soil, it can be explained in terms of density. So we all know that the density of the water is 1,000 kilograms per cubic meter, but on the contrary, the density of the water vapor is approximately 1 kilogram per cubic meter, which means that there are at least 3 orders of magnitude in differences in weight between the water vapor and the mass vapor. That this makes this assumption more than reasonable. The other aspects I have been focusing is this Kelvin law here. So you see suction depends on both temperature and relative humidity. But if we try to plot this equation, what we find here, we found that the suction really depends on the relative humidity. So it changes by about 550 megapascal in the whole range, while on the other side, from 0 to 100 degrees of changes in temperature, the changes in suction are really modest compared to the changes induced by the relative humidity, which in mathematical terms means that the variation of suction due to temperature is much smaller and that negligible of the changes in suction due to the relative humidity. And for our simplification purposes, this means that we can neglect these terms here in the liquid water flow. So we neglect these terms as well, and we get the final form of the water mass balance in this shape, which is much easier to handle also to implement a numerical code and understand where possible problem may arise. The other results of our preliminary investigation is that the liquid water flow, which is described by these parameters Kw, and this depends on these parts of the equation here, plays a major role in the agrothermal coupling compared to the water vapor flow, which is the diffusivity tensor in here. And for us, this means that we need to carefully characterize the liquid water flow, while we can assume, without any significant error, as a simple tortuosity model for the vapor diffusion. And by simple, I mean that you can use standard literature solution. But let's now start to understand a little bit more what is the role of the soil, the moisture in this type of problem. So we need to characterize the storage term in here and also the liquid water flow in this part here. Luckily for us, the storage of liquid water and the liquid water flow, they both depend on the amount of water that is present in the soil, that can be described by the degree of saturation, the water content, SL or WL, but also depends on the way it is distributed in the pore network. And this is often called the water retention curve. So these points here represent experimental points that relates degree of saturation to relative humidity. And here I have reported also some suction values at some relative humidity values. The good news is that we can fit this curve here, this experimental point by using a mathematical law, which is called the Van Genuchten law, that gives the unique relationship between the degree of saturation and the relative humidity. The other good news on this of this modeling is that with the same parameters, they are just free in general, you can also model the evolution of the liquid permeability with the relative humidity or the degree of saturation. And what this equation tells us is that when the soil, our material is fully saturated, the water can easily flow through the pores. This is because there is no air. But as soon as we start to desaturate our models, we get a significant drop in the liquid permeability because some of the pores are obstructed by air and the water cannot flow through these pores. And if you want to see that in the other way, what happened to the water vapor, well, it's the same thing. When the degree of saturation is very low, that means when the relative humidity is low, the vapor can easily flow through the medium, through the pore networks. But as the soil approaches saturation, you get a drop in the vapor diffusion that really drops to zero, because when the soil is fully saturated, there is no air, so the air cannot pass through the medium. And this is what is described by the simple tortuosity model, which has been used also to study the desiccation of soils, such as the study of Guida et al. In 2023. So this was for the hydraulic part. On the heat transfer in soil, so this is the thermal balance we need to solve, and I have already commented the water capacity, the water storage, as well as the liquid water content here, the liquid permeability here, and this is the phase change of the liquid water during the evaporation and condensation processes. Then we need to define the thermal parameters, and thermal parameters in general are highly influenced by the soil mineralogy, so it's not you need a specific test to evaluate them. But for instance, the equivalent heat capacity of our soil, which our domain, which include the soil, the water, and the air, is nothing that a volume average of the heat capacity of the single species, such as solid, water, and gas in our domain, which means that only unknown is the heat capacity of the solid particles, these parameters CPS here. On the contrary, for the thermal conductivity, lambda, which is again is a function of the amount of water we have in our model, what it is observed from experimental data. These are data collected by Losini et al. You see that the thermal conductivity increases with the water content, and this again is reasonable because the water is a very good conductor. So the more water we have, the higher is the thermal conductivity, the global thermal conductivity of our material. And in the other case, you see that the dry thermal conductivity, which is the thermal conductivity of the soil particle, increases by increasing the density, because the conduction works better if the soil are in better contact. And this is what you get when you have a high density in your samples. So this is a linear trend. So to be honest, we just need to know the dry density, the thermal conductivity on of the dry soils, and this slope that you can see is pretty much constant if we take out from the group these purple points in here. So just coming to the conclusion, and then I'm going to show you some results. We have, I hope you understand why we can simplify our models, that finally reduces to these two equations here that can be solved if we know a given number of parameters. And for the solid particles, we need to know the porosity of the materials and the density of the soil particles, which is usually pretty much constant, around 27,000 kilograms per cubic meter, which means that we have two, or we can also say one parameter for the solid particles. Then we have four parameters for the hydraulic part, and three of them are the water retention parameters, for instance, that are the same that describes the evolution of the liquid permeability with the degree of saturation. In addition to that, we need to compute and evaluate the saturated permeability, K-SAT, and this can be done with a very standard and traditional odometric test in a geotechnical lab. And finally, we need to quantify the thermal properties, for which we need three parameters, as I said. So we need we need the specific heat of the solid particles, the thermal conductivity of the dry soils, and the thermal conductivity parameters, which is the slope of the trend that you have seen before. So with a number of 7, 8, or maybe 9 parameters, we can solve our problem. And this, now I'm going to show you an example of this hygrothermal coupling. And to do that, we started with a very simple model of an infinite wall. And under this condition, assuming that there is no influence of gravity and there is no capillary rise from the foundations, the problem simplifies and reduces to a simple one-dimensional models. And also, we are assuming that the boundary condition that is defined in terms of thermal flow and water vapor flow at the boundaries is the same both on the left and on the right of our wall. So if we do that, we can study just half of our model. On one side, we apply the boundary condition here, and the axis of symmetry of our model is an impervious boundary, obviously. And we played a bit with the perturbations, and we applied an hydraulic perturbation here, in which we kept the temperature constant, and we changed the relative humidity on this boundary here. And obviously, we made the other way around. So we kept the relative humidity constant, and we imposed a daily variation of temperature at the other boundaries. The results I'm going to show you in the next, they will be all of them, they will refer to the center of the model, so the impervious boundary here. And let's now try to have a look at these results. So these are the results from the hydraulic boundary conditions in which the temperature has been kept constant and the relative humidity changes. What it happens is that at this point here, after one point, the soil starts to dry. So there is a reduction in the relative humidity. And this is because the imposed perturbation is globally a drying process. And this process depends also on the initial values of the temperature in our model. But what is interesting here is the coupling term. So what happened to the temperature when we are imposing just a change in the relative humidity? What we get here is that in the first 100 hours of this simulation, we observed a reduction in temperature at this point of the model here, which is also function of the starting point of the initial temperature values, which means that the higher the temperature, the higher is the coupling that we have in our models. And if we have a look on the other problems, so the thermal boundary condition, we observe two things. First of all, the coupling is significantly smaller, which means that you see the temperature reduces by about 10 degrees at some point, and this change in temperature of 10 degrees corresponds to a very little change in relative humidity of about 0.5%, which from an engineering perspective is practically zero. And what is important also to note is that this direct problem here is not really influenced by the initial values of relative humidity, but the coupling, even if little, yet it is influenced by the amount of water, the amount of relative humidity we have in our samples. So, on the concluding remarks, I hope in this brief presentation I give you an idea that earthen materials are a multidisciplinary and multi-scale field of emerging interest that in particular involves geotechnical engineering, structural engineering, but also material engineering and physical engineering for the indoor comfort. And on top of that, there is also a very good interaction and connection with chemistry for the stabilizer, but also with architectural side for the preservation of our historical and cultural heritage on this earthen structure. And in our opinion, where the research should go now, it should try to find a novel stabilization methods that at the same time will provide low environmental impact, but still increasing the performance both under low mechanical loading, but also under hydrothermal loadings, which by means now it should be expanded, and these numerical that at the moment are consistent and comprehensive, which means that they are able to describe the main aspects of the hydrothermal coupling. Now they should be used to assess the quality of indoor air in earthen structures. And also, but this is not really geotechnical, this is something that other engineers should do, but is a suggestion that I think is very important in this case also. We should try to assess the life cycle of earthen structure by considering all the aspects from the sourcing of the product to the end of life, because this could also help us to inform on the choice of the stabilization method that we may want to use or we may not. And finally, obviously, we need to explore new construction technique with no fear of exploiting digital manufacturing or also some artificial intelligence stuff also in this case. Well, this was pretty much all. I just want to acknowledge the other member of the research group at the University of Genova, that the person that leads this research group is Professor Domenico Gallipoli, which is shown here. It has been working on raw earth construction and saturated soils for many years. And also Dr. Agostino Walter Bruno, which is an assistant professor at the University of Genova as well, and is the guy that's really worked on the structural performance of earthen structure from a geotechnical perspective. So if you want to expand your knowledge, or if you want to work on this, on other geotechnical topic, please feel free to contact us and drop us an email, and we can arrange a discussion. Thank you very much. I have concluded. Gracias a todos.
Muchísimas gracias, doctor Lalicata, por la presentación tan interesante. Ahora vamos a pasar a una sesión de preguntas. Recuerden lo que les dije al principio, que simplemente levantan la mano y cuando se les da el turno pueden entonces usar el micrófono para hacer su pregunta. Puede ser en inglés, puede ser en español, para que puedan hacer sus preguntas. Alonso Poveda, el profesor Alonso Poveda tiene una pregunta. A favor, utilizar el micrófono.
Gracias, buenos días, doctor Rafael. and thank you, Dr. Lalicata, for your presentation. I have two questions. The first one is about the minerals in soils. Which minerals have the most influence on thermal properties?
Well, usually the clay aggregates. So there are some minerals that they are present, not really the silica part, but all the things that are in the clay particles. So this is very important because for what concerns the more coarser side of our sample, this is pretty much constant. While some clay minerals, they can really have different thermal properties. But this is still quite, I mean, from a geotechnical perspective, still quite unknown. So I'm still quite new to which is the best type of clay you want to have. If you want to have a high thermal capacity or low thermal conductivity or whatever is the parameters you want to optimize in a way. But also, as you say, as I said before, the earth is the main benefit of using earth as a construction material is that it's locally sourced. So in most of the cases, most of the times you cannot really control your mixing, because if not, you are reducing all the benefits.
Okay, thank you, Doctor. And I have another one about the hygroscopic and temperature regulator properties. Are they preserved over time?
Mm-hmm.
Okay, perfect. Thank you.
Yes. Well, the problem is thank you, first of all. So, well, the problem is that you are not having thermal equilibrium. You don't have equilibrium because, oh, sorry, can you hear me?
Yes.
Hello?
Yes, I'm here.
Okay, because I'm seeing that there are some problems with
some delay
with the connection. I'm sorry for that. Okay, so the problem is that the environmental condition, they change during the day and during the night, but also they change during the season. So you'll never get the thermal equilibrium. So that in general, you always have this absorption and desorption, evaporation and condensation processes that happens whole day, whole month, all weeks, all years. So you don't get to saturation that way, because the environmental condition is always changing.
Thank you.
Thank you. Thank you for the question.
Gracias, Alonso, por sus preguntas. Ahora tenemos al profesor Andrés Aray.
Okay, buenos días. Thank you, Dr. Leonardo. I am the director and I really appreciate your presentation. And I would like to thank to Dr. Rafael Baltuano for making this possible. First of all, it's very interesting because during this week, we have been discussing about circular economy, or why it is important to change the paradigm to not use just historical data and to include prediction through modeling, for instance, to assess topics related with climate resilient infrastructure, that kind of things. Your presentation is related a lot with this kind of topics. I really like when you said the modeling, the first question that you make was what is important and what is not. I really like this part of your presentation. That is very important. And I have two questions, specific questions, because I am very interested about the compressed bricks. Obviously, we would like to test new material and explore new construction techniques. The compressed bricks is like a Lego, okay? You explain about stabilizers and you use biopolymers. In my experience, my field of action is water treatment, and I already use biopolymers, specifically the Triumphida symmetrioba. It's a leaf of a plant. It's very popular. It's very popular here in Costa Rica. We call mozote. I really like to put on a student to assess that kind of biopolymers. But where I can find more detailed information, or perhaps you can detail more about how make the compressed bricks. What do you think about test this biopolymer? Because we're using in coagulation flocculation process, but perhaps it can be used here as well. This is my first question. Thank you, Doctor.
Okay, so I must admit I'm new to the experimental part. I mean, I've done a lot of experiments, but on the geotechnical perspective. We have starting to do experimental camp on stabilizers here at Genova, because we are setting up the lab. And our students, they are using URGAM, such as Bruno used that in his thesis, Dr. Bruno. And I have shown the results of his PhD thesis, actually, in the presentation. So the way we prepare our sample with the stabilizers, we add the percentage in weight. This is in form of a dry powder, also the guar-gum. So we add that like in 2-4% of mass of the dry mass, obviously, and to allow the process to occur, to take place, we add a little bit more of water. For instance, we add 1% water more than is required for the optimum water content. We mixed everything and we left the stabilizer to cure, I mean, to act, to start the reaction for at least 1 week before preparing our samples.
Okay,
at least 1 week. At the moment, we are trying to be consistent, which means that if we wait for 1 week for the cement or the lime, we wait the same amount of time for the biopolymers.
Okay, okay.
Just to try to compare similar things.
Okay, thank you. My last
we
question.
are still exploring.
Okay, okay. Okay. My last question is about console. Do you think that it is enough?
Okay.
Has a numerical modeling, or it could be a future work trying a different method?
I think console has a lot of advantages because it's very flexible, which means that you can implement your system of equations the way you like. Obviously, if you go out from the pre-built physics, so if you go on the mathematical physics, which means they are just basically the differential equation systems, you can write what you want. Then the problem of that is that you need to be sure of your results, and this is why I've been focusing a lot on what is important, what is not, because the first time I saw this equation, I was really scared. How I can get an error if there is some. As long as you are in the validation phase, more or less it's all good, because you have your data, you can compare your data and see, okay, this is good, this is not good. But when you want to explore new scenarios, you need to be really sure of your model. So the simple, the better, in my opinion, as long as it allows you to model and describe what you want to describe. But in general, I will try to keep it simple also with numerical model. And console is a good compromise of that.
Okay, okay. Okay. Thank you very much.
Thank you. Thank you, profesor.
Gracias, Andrés. ¿Alguna otra pregunta? Mauricio, profesor Mauricio Araya, por favor.
Okay, thank you very much for your presentation, Dr. Lalicata. I have a mandatory question. What recommendations can you give us regarding the use of these materials in a seismic country? Okay,
so thank you very much for this question. When I was preparing this lecture, I was trying to also try to answer sort of this question, because this is the question my colleagues in Italy, they always ask me. So how do you deal with seismic areas? Well, first of all, maybe one of the answers is given in the picture I was showing at the beginning, which is showing the widespread of earth and construction all around the world. So yes, obviously they are, as you can say, they are not very strong construction materials compared to concrete or others, or steel, for instance. Obviously, they are not strong. They're not well. They are ductiles. They are not brittle, but they have low low resistance. But you can, if you want, you can improve that by obviously increasing the size, which is why so many historical sites are still there, because they have very massive walls and also foundations. So this is the first answer. Second answer is that we need to study more, because there is people in Portugal as well as in Italy which are starting to study the seismic behavior of earth and wall panels, because they have earth structures in Portugal as well as in Italy. They are starting to assess the seismic performance of these structures, which obviously they are more exposed. This has to be said anyway. But yes, there is a lot of work to be done, because it's not very clear at the moment what will be the actual performance. So there is experimental and numerical modeling of this area as well that is developing. But this is more from our structural techniques than geotechnics.
Okay, thank you very much.
I hope I answered your question.
Okay.
Gracias, Mauricio. ¿Alguna otra pregunta? Well, I have a couple of questions while they think about it. Two-part question related to the construction of the bricks. You show some plots that you increase the compactive energy. And I was curious, how do you actually increase that compaction energy? And related to that, if you have any cyclic testing on shear strength in order to assess some of the dynamic properties, or if any or all of the data is static.
Okay, no, thank you for that question, Rafael. So the first question, you can increase the energy. Well, you don't have to think necessarily to a dynamic compaction, because that tests they were made by static compaction, and by static compaction you can increase the energy you want, as long as you don't break your mold. But yes, so the way the energy was increased was via by a static compaction. And no, we don't have any dynamic test at the moment. We have just uniaxial compressive strength, because it's the first parameters you want to assess in this problem. But obviously, yes, I agree with you. It is a very interesting, and in the very first step from a geotechnical perspective, to characterize the seismic performance of the wall. So there are structural engineering that work at the wall or panel scale, but we could work at the material scales by characterizing the dynamic properties of our samples. Yes, absolutely right.
Thank you for that answer. I have another question. You show a table where you show the parameters we need to model numerically the problem, and I want you to let me know, what do you do with the vapor diffusivity? Because I don't see that parameter in the table. How do you assume the value or estimate that value? Okay, so what I was talking about, the simple viscosity model, the idea is that we know the diffusion of water, of vapor in the air. I mean, in a room like the one we have, this is known, is a slightly function of temperature, but this is, again, it is known. But when the water has to flow through a porous material, obviously you get a different diffusion, because the flow is obstructed by the solid particles. And the simple viscosity models give you the relationship that describes this hardship that the
the water, the diffusion, the water, the vapor has to pass through the wall. So, and this is well described in literature. So the only parameter you want to have is the diffusion in the air, and that is an equation. It's a simple equation that requires the porosity and the degree of saturation. You need to know which is the amount of water, and by contrary, which is the amount of air you have in your voids.
Perfect. ¿Tenemos más preguntas? Última chance. ¿Alguna pregunta? No. Well, we want to thank you, Dr. Lalicata, for your time or your effort preparing this presentation. Really nice, very interesting, and with lots of ideas for future research. And we hope we can probably do something together in the future on these and other topics. And thank you for being part of our 50th anniversary, the Construction Engineering Department at the Costa Rica Institute of Technology. And thank you very much. Thank you to everybody that attended for your time, also your questions. So that's it. Thank you very much. Bye.
Thank you very much. Thank you very much all. Thank you, Rafael, and thank you all for listening. I hope we can really collaborate soon. Thank you. Bye.
Thank you. Bye.
Bye-bye. Bye.